So, hello everyone. Welcome to part one of our short simpulse webinar series, The Importance of Being Unified. My name is Alexander Walser. I'm honored to welcome you in behalf of the ASCS Association. We bring together or connect people, ideas, and technologies in the ASCS and want to foster collaboration, knowledge sharing across the automotive and mobility sector. And in line with this mission, we will learn today in this session about the benefits of using a unified data model between design and simulation. And in part two of this series, this will take place on the 25th November. We will showcase real-world use cases covering the full spectrum from early-stage design simulation to validation and manufacturing simulation. So it's my pleasure to introduce our today's speaker from Dassault Systems, Daniel Valicotti. Daniel is an experienced industry process consultant at Dassault Systems, helping customers implementing industry-specific simulation solutions and workflows using Simulia and 3D Experience platform. He's an expert in finite element analysis and computational mechanics with a specialization in multi-scale material model for functional materials. Daniel advises on simulation methods and solution strategies to optimize energizing processes and enhance product performance. And with this short introduction, I hand over to Daniel. If you have any questions, please feel free to write them to the chat, and we will go through them after the presentation. So Daniel, the virtual stage is yours, and we are looking forward to your presentation.
Okay, perfect. So thanks. Good afternoon. Welcome everyone to, as Alexander said, part one of this mini webinar series called The Importance of Being Unified, in which we are going to discuss how the, say, seemingly trivial design or detail of a defined unified data model between modeling and simulation actually has a huge or significant impact on both design and validation, and how it can really transform product development processes. So as Alex said, my name is Daniel Valicotti. I'm an industry process consultant for the transport and mobility industry at Dassault Systems. And together with my team, we support our customers from the automotive and rail sector in Central Europe regarding our simulation solutions. And in today's part one of the series, you will learn about our technology, while in 2 weeks, in part two, we will showcase some examples from design towards manufacturing, as already explained. So for the agenda of today, we start with the industry challenges and the why we need to act, and then we follow up by a comprehensive overview on our ModSim approach from a technological and a process point of view, and I'll close with a summary and a short outlook. Now, the automotive sector in Europe is under pressure. That is nothing new. You heard about it almost every day in the news. It ranges from intense global competition, investment in energy transition towards battery electric vehicles, increasing environmental and safety standards of the EU, and many more. And question is, which engineering challenges are derived out of that? And first and foremost, I would say there's an increasing need to speed up development. The global market, especially competition from China, is moving faster than ever, which means that Chinese manufacturers are bringing new models to the market at an incredible speed, forcing us to rethink how we need, or how we develop, how we test, and how we launch vehicles, such that if we can't accelerate our processes, we risk of falling behind. And another major challenge is siloed engineering. All too often, our teams work separately. So we have the mechanics, electrical departments, software departments, each focused on their own areas. This isolation slows us down, makes it more difficult to achieve true system integration. And we are also dealing with immense data complexity. Development of modern vehicles generate massive volumes of data, from geometric data, simulations, sensor data, real-world testing, you name it. And managing and interpreting and connecting the data across multiple teams and systems is a constant struggle. And finally, the level of expertise required continues to rise. Today's vehicles demand deep cross-disciplinary knowledge from software to material sciences, energy management, and so on. And bringing that expertise together efficiently is a major task. And while all of these are, let's say, general challenges, this is also true for simulation or for the simulation domain in total, as the customer statements underline. Now, furthermore, if we think about simulation processes and how to get more efficient, we need also to think about the significance of simulation, which is rising every day because there's a shift from the validation certification strategy in the companies. Traditionally, companies relied on hybrid approaches, a combination of simulation and extensive hardware testing, which of course has given a lot of confidence, safety, and performance and compliance. But it's also time consuming and very costly. And now the industry is shifting towards a simulation first approach, where most validation happens virtually with only critical stages confirmed on physical hardware. And to not hinder the potential in time savings that comes with this change, we need to make sure that simulation is well integrated in the development process. Now, when we talk to our customers and domain experts, one of the major challenges to ensure performant and efficient simulation processes is the synchronization and exchange of data. The best tools, the best automated workflows, all of them are meaningless if the underlying data is not up to date. And modern vehicles, of course, are incredibly complex systems that bring together mechanical design, electronics, software, and data from countless sources. And each team, from, let's say, design to simulation to manufacturing and testing, each team works with a huge amount of information, often using different tools, different formats, different processes. And the problem is that this information doesn't always stay aligned. So that a small change in one domain, for example, a software update or design modification, might not automatically flow through the whole process to the others. And this leads to inconsistencies, reworks, and also delays that we, of course, cannot afford. And especially as the development cycles accelerate or need to accelerate, keeping all teams and systems synchronized becomes even harder. The pace of change means that outdated or disconnected data can have real consequences, which means from design errors to integration failures and costly late-stage fixes, of course. And that's why information synchronization is now a top priority for most companies. Companies are investing a lot of money in integrated data platforms, model-based systems engineering approaches, digital thread, digital continuity to connect every stage of the process. And the goal is to have, in the end, a single source of truth where every engineer in every domain works with the up-to-date data and consistent information. Which brings me directly back to the title. That's why we also chose it, the importance of being unified. Now, what does it mean? And so let's have a look how we approach these challenges with our ModSim technology. And this will be the overall slide that we will see a lot in this talk, and we will enhance or add different topics to it. First of all, let's talk about the technology. So what is ModSim? So ModSim, at its core for us, it's a unified data model. So it's the unification of modeling and simulation, two disciplines that we believe need to be interwoven for efficient workflows. So on a common data model with a single user experience within the 3D Experience platform. And within this webinar, I'm going to explain the concept and the technology behind it. As I said, while in the beginning, in part 2 of the series, we will show more of the ModSim in action from design towards manufacturing. All right, let's look at the way that this ModSim technology works. And we start with what we call our ModSim loop. And the best way to highlight this is to compare ModSim to the traditional CAE approach, where we create our own design and then we export our model. We do some geometry cleanup, maybe export it again, do some meshing, connection elements, you name it, boundary conditions, loads. Then again, we usually export it into a simulation setup, and then we move it to the HPC cluster to compute. And then in the end, have the post-processing and feedback the results to the designer. And as you can see, there's a lot of data transfers and data breaks in between. And this is, of course, a challenge. But also, when we want to do a design iteration, so if the simulation results do not fit to the requirements, we find that we will need to go back to the designers and have to repeat all this process again, which in the end can take quite a lot of time, even though it's highly optimized or automated. Still, it takes quite a lot of time to run these iteration loops. And in comparison to that, if we look at the ModSim approach, we will first see that once we have our design, we are not exporting that 3D model. So we are building the CAE model on top of the CAD, and which leads to very quick design iterations, because if we have changes in the CAD, the simulation engineer directly gets informed and can also update his simulation object. And then we can iterate really fast between design and simulation, as both of them are built upon the same data model. And so the whole design, validation, and iteration process can take maybe days rather than weeks, so speed up the process by quite a lot. So this is the overall idea behind ModSim. Now, why does it work? Let's dive a little bit deeper into the data structure to better understand why this model is capable of doing what I just highlighted. So let's focus first on the modeling side. We go through the model loop. And here it really doesn't matter which phase we are in. We will ultimately end up with a 3D design comprising of assemblies, parts, materials, features in general. And now if we want to build a simulation upon it, what we do is we just take the model again, and then we enhance it with everything that is needed for simulation. So we choose the reference geometry, we add an abstraction shape for geometric cleanup, we add our mesh to the parts or to the assemblies, then we add connection elements to the mesh, and then we build up our simulation scenario. So we're going to add a simulation object all around that, which includes both the boundary conditions, initial conditions, loadings, and everything that is needed from a simulation standpoint to run the simulation. And once we've done that, we can, of course, solve. And the results then also get directly stored within the simulation object, which means in the end, instead of having CAD data, simulation data, and result data, everything is stored within a simulation object. Everything is in one place. We have a single source of truth, and everybody can access it if needed. So based on the results, we can create a report, and then we can funnel that back to the design. And if now a design change is needed, you can see it now highlighted in the light blue. The designer can change his cut geometry. The simulation engineer gets notified that a change took place, and then by the push of an update button, everything simulation related, simulation model related, gets updated, and the simulation can be rerun. And these iteration loops, as we said, can be super efficient and run very fast. Okay, now explaining technology only on the base of a data model might not seem too intuitive. However, it is really important to understand how ModSim is capable of performing. And now let's have a closer look on the process level, what it means for simulation processes. So on a process level, we have 4 specific layers that hold true for all applications and workflows, namely unified process, automated process, democratized process, and traceability or traceable process. And we use a simple example as a demonstrator to showcase all of these process levels. So first of all, unified processes. So what does it mean? As highlighted, ModSim is based on a unified data model. So there's no data transfer as it's a single environment, no separation. So what it means is, in this case, if you're a designer and you've created a model that you then want to qualitatively assess, you don't need to move applications. You can just enhance your model within the same environment and build a simulation on top of it. And we have a short video to demonstrate it. So here a designer basically wants to build the simulation object. And for that, he starts with an envelope of a brake rotor that he then manipulates to create a new variation of this brake rotor using his CATIA toolset, for example. And that's the mod part. Now, if they then want to perform a qualitative validation, so the sim part, what they do, they just change within the simulation environment. They create what's called in this case a modal analysis, and you can see that all what they're doing is basically selecting an app, creating the finite element model based on some standardized methods, on automated methods, and then they select what kind of frequency range they want, and then they have their analysis and results. And this can be done, as I said, really fast, super efficient within the same environment. Now you might argue that designers don't want to build up their finite element models themselves. It's not their job, maybe. Or maybe they don't have the knowledge to do so. So for that, we can also create automated processes, automated simulation scenarios based on a dummy or a construct model that the designer then can just replace with the actual design model. And then everything else is built up in the background and is ready to run again. So we can also have a quick look at that. So here you can see a simulation for a brake rotor, and it's a rotor torque analysis. And the designer basically just has to choose the new design variant that he created and replace the old one in the simulation. And everything else, the meshing, the boundary conditions, the loading conditions, everything is updated automatically, and the simulation is directly ready to run again. So he doesn't have to put his own knowledge, his own understanding of simulation into this object. He can just use it and replace the geometry. One further layer of abstraction is democratization. And here we are using the technology which is called engineering templates. And within these templates, any kind of simulation, no matter the complexity, can be built and stored and made accessible through a user interface. Such that, again, the end user just needs to drop in his design, replacing the placeholder geometry, and the simulation is rebuilt automatically. And this is not only useful for designers, but this could also be used by experts who want to standardize certain simulations that they have to do several times, or maybe to exchange IP within the company. So instead of creating the model based directly on the design model, we build, again, a dummy geometry where the simulation is built upon, and then we just replace this dummy model by the design model and can rerun the simulation as is. And here you can see that in action. So basically, we can choose a template. This is an easy GUI where you can just replace certain parts that have been pre-specified. Then you search in the database for the part, and then you load it in. And in this case, a brake cooling simulation is built up automatically. And you can see that everything related to that, so the fluid domain and the rotating geometry, everything is defined, and you can just run the simulation and evaluate your results. Now, these presented layers, 3 of the 4 that I just shown, are all layers that deal with generating new data and validating current designs. Now, however, one of the major challenges we spoke about is the data synchronization and exchange, which leads me to the 4th layer, which is called traceability. And ModSim being part of the 3D experience platform means that it can take advantage of the relational data model that is the foundation of the platform. This means that the model is, or its components and the simulation, they are all linked via a digital thread and based on a single source of truth. So it's super easy to keep track. And we, of course, can manage and update the life cycle of these objects. So in this example, we again see the break rotor, and the analyst, for example, said that the results do not fit to the requirement, and the designer has to reiterate. And for that, the designer can just take the geometric object, do a new version of it in the lifecycle management, changes the maturity state, and then can just build upon it, create a new variation, forward the variation to the analyst again, and he can then rerun the simulation. And in the end, this traceability, as you can see on the right, from the geometry to the simulation objects, also to the requirements, all of that is built up automatically when using this approach within the 3D experience platform. Okay, so that is these are the fundamentals of ModSim processes. Now let's have a look what that means for what we call advanced applications. So this is just the basis. What else can we do with ModSim? One application could be, for example, generative design, namely non-parametric optimization. And I mean, this technology is there to find innovative topologies or different shapes to save material or increase stiffness, which is in theory nothing new. However, in an environment of ever increasing requirements, it is more relevant than ever. And here the workflow requires the collaboration between the CAD designer and the simulation analyst. So the CAD designer has an initial design or design space that serves as the foundation of a non-parametric optimization, for example, executed by the specialist. Then a mesh-based optimization variant is created that then needs to be reconstructed by the designer in the CAD tool. And this step is quite tedious. It takes a lot of manual work. It takes quite some time and thus reduces the efficiency of the workflow by quite a lot. And then also the reconstructed geometry again has to be forwarded to the simulation analyst, who in the end validates the new design. And maybe there needs to be some changes, some iterations again. So there's a lot of steps in between the design space and the final product. Now with ModSim, or having a unified environment and data model, this process can highly be increased in performance as the exchange between the departments is either obsolete because the designer can do the simulations by himself, or at least drastically reduced because the simulation analyst directly can share the data instead of exporting a mesh, for example, or importing CAD geometry that he has to build his simulation object on. And also here, let's have a quick example how it could look like. In this case, we again take this break rotor and we do a topology optimization and shape optimization. In this case, on the not on the disk, but on the caliper. So here, this is the initial caliper. This is the design space that we want to work on. And either the designer themselves can create the optimization model following the concept of democratization, using a virtual assistant that supports the users in the steps necessary to create the respective analysis, or he can just give the model to a simulation analyst who can build up the model. Then, of course, applying all the boundary conditions, building up the scenario, and then running the simulation, or in this case, the optimization. And then you end up with a tessellated geometry in the first place. It can look like that. But the magic happens then with this little button here that is called generate. If you push that, then your tessellated geometry directly gets transformed into a cut geometry. This is a cut part now. And you can see you can use this cut part directly in the validation. The use case is already built because it's the same use case or simulation case as in the optimization. And so the validation step is also automatically done. And then you can even use this cut part directly in context of CATIA to further change something if you need to, and then you just replace it in your in your overall assembly and end up with the optimized topology. So no iterations really needed between design and simulation, or if there's an iteration needed, can be very efficient because both of them are working on the same data model. Now, everything you saw up until now could be realized due to the benefit of having a unified data model and direct connections between modeling and simulation. You could, of course, argue that similar results, maybe besides the traceability aspect, could have been obtained by employing an associative interface between a CAD or maybe by scripting. And this is partly true, I would say. However, ModSim is not only about connecting modeling and simulation, but it's also about putting numerical validation in the center of product development. So maybe let me explain what I mean with that. So if we take a look at our traditional engineering customers, they have quite advanced products with many different layers of complexity that they need to manage. And they will also have many different data sources and potentially many different tools in place. And it's very difficult to manage the interoperability between these data sources and the complex products. So between these two pictures here, basically, with a number of different tools. So of course, by putting all of this together in one place in the 3D experience platform, for example, we can achieve a single source of truth, not only for CAD and simulation, but also for every other data needed in that process. All of it within the system and all of these processes and people together working in one place. So how can that look like? We end up with this onion diagram of our ModSim workflow, connecting different layers of a typical organization and the data that is important for the respective departments. And in the middle, we have modeling and simulation. So this is the core ModSim idea that I've just shown. With the CAD data, with the simulation data. But this is then directly connected or can directly interact with the test management, for example, where we have our validation and certification strategies and apps and process automation tools. And then around that, we have the product management, where we have our requirements, our architecture, as well as our change management. And around that, one layer on top, there is the governing based on the project management, for example, where we have project management tools, task management tools, and tools to allow us to collaborate with each other. And ModSim, as I said, is in the center of it, seamlessly integrated in the whole process. Now, with that in mind, let's take a look at connected validation. So what are the benefits of working in that kind of environment? So first of all, as I said, we have ModSim. This is well understood by now, I would say. Here we have the designers, we have the simulation engineers, and every information needed for these two departments related to our end-to-end simulation, the models, the simulations, the results, everything. And in this case, we take a look at multi-physics simulation for an e-machine. And the designer, as well as the simulation engineer, they are directly connected or are part of the validation and certification strategy, and thus are directly linked to the different test cases. And these test cases, they link the requirements to the analysis, and they track their progress and they track their results. Because of course, we don't just simulate for the fun, we simulate to validate our requirements. And this is the link that connects the both worlds, requirements to simulation using test management. Question is, where do we get the requirements from? So from a product management layer, the functional and non-functional requirements are defined, for example, based on a model-based systems engineering approach. And thus, we end up with a full traceability from the customer requirements to the functional, logical, and physical object. And this can, for example, be followed using an impact analysis to see if we change either of those objects, if we change something within this link, then everybody else gets informed that is directly connected to the change. All right, next process, maybe in this case, last process, but definitely not the least, let's have a look on how ModSim also enables machine learning. Machine learning, of course, a topic that is quite prominent these days. So how do we fit into this context? Now, when we talk about machine learning, oftentimes we focus on the algorithms, neural networks, decision trees, deep learning architectures. But the truth is, no algorithm can compensate for poor data. So the real foundation of any successful machine learning system is well-structured data. And with well-structured, we mean that data is organized, consistent, complete, and especially relevant for the respective use case. Now, we understood that with ModSim, we are able to efficiently create, simulate, and store our data, employing the principle of single source of truth, and fully embedded in context of product development, with a traceability from the requirements down to the manufacturing, and which is exactly the kind of data that we need to feed into our algorithms. And based on this data, we can then build our machine learning models, which in the end means, for example, in context of simulation, also following the idea of democratizing knowledge and enabling designers, for example. One use case could be the creation of so-called surrogate models that are able to predict field data for 3D simulations. And here, ModSim is used to generate the training data based on a parametric geometry and a design of experiment study, for example, such that we end up with a lot of data points we can feed into the algorithm. And based on that, we can train a machine learning model that then can predict the behavior on further designs that we want to check, which of course further accelerates the designer's workflow if this is shifted towards a designer, or supports the work of an expert when he can just move around the parametric space and directly gets the results instead of setting up the simulation and needs the simulation to be rerun. All right, with that, let me come to the summary and maybe some kind of conclusion. So within the first part of the webinar, as I said, we wanted to lay the foundation to show you that later on what kind of applications can directly benefit from ModSim. And what we demonstrated here were the implications of a unified data model on both the modeling and the simulation. And we highlighted the capabilities of our ModSim approach in context of complex product development processes. So what we did is we talked about the 4 process layers of ModSim, namely unified, automated, democratized, and traceable. And we have seen the advantage of our advanced ModSim applications. In this case, we took a look at generative design. We position modeling and simulation in the core of a connected validation strategy, so linking simulation to the disciplines test, product, and program management. And finally, we also teased some machine learning supported applications to further speed up the development process. But this, of course, will all be talked upon in more depth in our second part of the webinar series in 2 weeks. But maybe closing the bracket to the initial challenges that I presented, we think that simulation indeed, or especially embedded in a collaborative environment, can be the tool of choice to drastically reduce development times. But from our perspective, the crucial part here is the unified data model, which is the backbone of an automation, integration, and democratization strategy that in the end really helps to speed up the design process, the development process, and really can tackle the challenges that we saw in the beginning. Okay, one last time for today, I want to show this overview slide. So today, we learned a lot about the first 2 lines. We learned about technology, and we learned about the processes. Now, in 2 weeks, what we want to do, it's on Tuesday, the 25th of November, also at 2 p.m. My colleague Andreas Renner and I, we dive deeper into real-world applications, showing different methods and connecting the worlds of design, simulation, and manufacturing. And I'm really looking forward to meeting you again there. And for now, if you have any questions, feel free to ask or contact me afterwards. And yeah, I thank you for your time, for your attention, and please, let's share experiences, post your questions. We still have quite some time left. Thank you.
Thank you very much, Daniel, for this overview and introduction to ModSim. So if you have any questions, please feel free to write them to the chat, and then we go together through the questions. So I think the benefits of ModSim were clearly explained, and maybe starting one question from my side. So however, in most companies, there are different domains, and these domains use different tools and data formats for modeling and so on. So how can ModSim be introduced in such an environment, and what would be a sensible approach to implement and test such a workflow?
Yeah, that's a pretty good question. This is the question that we usually hear from our customers too, because of course, the simulation domain especially is not a green field. It's a brown field where a lot of established tools are already placed, and a lot of let's say established workflows are there that are highly automated. In the end, it always depends. First of all, what is always possible is that, of course, we've seen a lot of structural use cases today, but our simulation portfolio ranges from structural to CFD to CST to EMAG to multi-body simulations. So first of all, what we can do is we can move a current process from a customer to or into the 3D Experience platform. Maybe in the first case, showing the capabilities of our solver, so translating the processes from a certain solver to our solution first, displaying what is possible to achieve. This is one way we can do it. The other way would be we can also include other simulation tools, or at least, let's say, the simulation results of other simulation tools, connect the CAD world to the simulation domain in an automated process, exchange data between third-party tools and the 3D experience, and build up a ModSim approach based on an integrated way. So this could also be possible. It really always depends on what the vision of the customer is, where he is heading, and in the end also which tools he's using.
Okay, great, thanks. So there's a further question in the chat. Thanks for the nice presentation. What do you mean by democratization in this context exactly? Is it only related to validation part of the V cycle?
No, it can be, but not exclusively. So democratization for us means we want to empower non-simulation expert users to use simulation tools in their daily work to, first of all, reduce the iteration loops between, for example, design and simulation. Because a designer builds a design, he needs to have a first idea whether design is fitting to the requirements. So he asks the simulation expert to do that. And this task lands on this virtual desk, the simulation engineer, and stays there for a while. But the designer needs the answer quite fast because he wants to continue his work, right? So it would be easier for him to do this qualitative assessment right on his own. And democratization means we want to provide the designers or whoever wants to use simulation with either the tools or the knowledge or the processes to do that on his own in a first qualitative way. And for that, either he can build up the simulation model himself, or, which is more realistic, some methods developer build up some simulation templates that the designer can directly use, and then he can just put in his new design idea into this template and gets a quite good understanding whether the new design approach fits to the requirements or not.
Okay, perfect. Yeah. Thank you, Daniel. I want to make once again the remark that in 2 weeks there will be the second edition of this webinar, where we also have a deep dive into some further use cases. So please feel free to sign up by scanning the QR code or look on our website. There you can also find the more information about this second edition taking place on the 25th November. So there are no further questions in the chat. Then once again, thank you very much, Daniel, and thank you all for joining this simpulse webinar. So don't miss to sign up for the second edition, and we are looking forward to your participation and wish you a great day. Thank you.
Thanks, everyone.